All right, take two. Let's see if we can get it to work. Okay, 5.2 and 5.3. I've said it in my Zooms. I think they should be put together. They're just a few different types of problems. But the beginning of this is some notation and formula stuff that you'll definitely need. So in the 5.1 video, which I posted, hope you probably already saw it, never mind. We had an addition rule, but that addition rule had a requirement. It needed them to be disjoint or mutually exclusive. This rule allows us to do it even if they're not disjoint or mutually exclusive. And I just want to give you a little visual of what we're talking about. So if that's event A and that's event B, and we start coloring, the probability of A would be all of this space. Wait a sec, you shaded in the middle. Well, that's part of A as well. It's just there is some in the middle that's A and B, and there's some on the sides that is just A. But all that whole circle is going to represent the probability of A. And then this represents the probability of B. And if you look in here, this middle portion got shaded or counted twice. And we want that to be part of our answer if it's A or B. But I don't want it counted twice, which is why we subtract. We include this minus the probability of A and B. I want it counted once, but the way I did it right here, I've counted it twice, and that's no good. So they just throw this on, and now I've got the general addition rule, and that does not require mutually exclusive or disjoint events. All right, conditional probability is big, and frankly, you've already really done this. When we did our conditional distributions in the tables with the Titanic and first class, second class, third class, male, female, how many lived, how many died, we did conditional distributions, and conditional probability is the same idea. Notationally, this is how you will be given a problem and know that it's conditional if they use this kind of notation. Otherwise, it's in the wording, and the wording can be a touch tricky. This is read, the probability of B given that A has already happened. And when we do conditional probabilities, this formula, and I'm not a fan of it, it kind of doesn't work for me, but there are some students who really like it, and it organizes it for them. So you decide if it works for you or not. But you go find the probability of A and B, which is just this, and then you divide that by the entire probability of A, which is all of that. So frankly, it's the middle divided by the circle. And we'll do some examples to clarify that. Well, likewise, in the 5.1, we talked about a multiplication rule, but that required the events to be independent. Well, now we have a general multiplication rule, and it does not require independent events. And again, for the probability of A and B, by the way, don't forget that means and that means or. You got to know both. You're going to take the probability of A, and you're going to multiply by the probability of B when I know, given that, A has happened. In reality, those two formulas are the same. I mean, think about it. If you just multiply both sides by the probability of A, don't we end up with this? So they're really the same formula. It's just kind of what are you trying to do? Are you trying to find the conditional probability, or are you trying to find the probability that they both occur? And lastly, and we'll spend a lot of time on this is going to take some practice. We will oftentimes be asked if two events are independent. Well, our way or our means, we can think about it and say we think they're independent, but our means of proving that they are independent would be to follow this. And I'm going to start on the right-hand side. If you know the probability of B happening, and you know the probability of B happening when A happened, Well, if that's equal to that, all it tells you is that A did not affect the chances of B happening. So this would be the mathematical way of us to prove that two events are independent. Again, we'll play with it more. We're going to use all that stuff in the next few examples, but I kind of wanted to get it all out of the way first. And now let's grind. Okay, so we got Rue and Du Bois are waiting to make partner at their law firm. Rue guesses that her probability of making partner is 0.7 and Du Bois' is 0.5. She also believed there's a 0.3 chance of them both making partner. Find the probability that neither make partner. Okay. So this is, you're going to have to, again, I've told you practice is important. You're going to have to kind of think about how the problem is presented to you, and then you'll start getting a feel for, wait a sec, this sounds like a Venn diagram problem. There is a chance that Rue makes partner. There is a chance that Du Bois makes partner. And there's a chance that they both make partner. Well, I'm going to tell you, if you can, if we give it to you, start with the both. Because we know that goes there. Now, here's the mistake that you always make. You say, oh, Rue's chance of making partner is 0.7. And Du Bois' is 0.5. This is wrong. Don't write it. Why is that wrong? Because if I add all of the options up, it adds up to more than one. And it cannot add up to more than one. So I know there's a mistake in there. Well, what's my mistake? The 0.7 we're talking about is that entire circle. Well, I've already got 0.3 of that circle, so that means this would need to be 0.4 so that the total circle is the 0.7. Likewise, this total circle needs to represent 0.5. I've already got 0.3 of it, so 0.2. So what's that mean? What's the 0.4? That's the probability that Rue makes it and Du Bois doesn't. 0.3 is they both, and Du Bois makes it, but Rue doesn't. Well, wait a second. Worth, you told me all of these have to add up to 1. I'm missing something. Well, not everything has to be in that Venn diagram. What the heck is that 0.1? That's going to be the probability that neither of them make partner. And again, I got 0.1 by doing 0.4 plus 0.3 plus 0.2, which is 0.9. 1 minus 0.9. That's the only other thing that could happen, and that does have a chance of happening, which is in fact what they were looking for. So a 10% chance that neither make partner. This is essentially the same problem, but I'm talking about people. It doesn't matter, people instead of probabilities. I could convert those people into probabilities or convert it in the end. It doesn't matter to me. But it's the same idea. We got some students taking physics, chemistry. 50 of them are doing both. I'm going to keep it in terms of people for right now, but if you wanted to change this to 50 out of the 200, you could. 70 are taking physics. You should be yelling at me right now. I just told you can't just throw that in there. 70 total kids are taking physics, so this has to be 20. And 120 are taking chem, so 120 minus the 50 is going to give me 70. Well, don't forget about the rest of the world. What could happen? Some kids aren't taking either. I know the total number of kids involved is 120, so 70 plus 50 is 120, plus 20 is 140. I think I said 120 was the total, but the total is 200. Sorry. So 140 taken away from 200 is 60. They wanted probability. I can't say 60 is my probability because that's bigger than 1. But I can go probability 60 out of 200, which is 0.3. I got a 30% chance of randomly selecting a kid and them not taking either chemistry or physics. Okay, next. And again, anything you don't understand, circle, and we'll come back to. So 5.2 deals with a lot of that. I'm going to come back to this example because 5.2 also plays with some of this stuff. And then 5.3 is the last example. So give me a minute. I'm going to bounce around a little bit. And this video is going to take a little bit of time because I'm kind of combining two sections at once. So first of all, I got to know what this is saying. And this is probability notation that you got to get used to. And when you read this, you're saying, what's the probability of randomly selecting somebody who is married if I know, given that they're in the 18 to 24 age group? So let's just say I'm a cop and I pull a young lady over and I look at her ID and it says that she's 22. I know she's in this age range. What's the probability that she's married based on this table of information? Okay. And again, you could do the probability of A divided by the probability of A and B. If you like that formula, go for it. I kind of like to conceptually understand it a little bit more. Well, what do I know? This back part is the piece I know. I know they are aged 18 to 24, which just eliminated all of those possible women. These are all the women aged 18 to 24. Those are the only people it could be. That determines my denominator. Well, of these women, which ones are married? Those ones. So 30, 46 divided by 12, 6, 14 will give me my answer. I'm not going to waste time with the calculator. You could figure that out and say, hey, there's a whatever percent chance of randomly selecting a woman who is aged 18 to 24 that is married. Or if I know that a woman is aged 18 to 24, there's a blank chance that she's married. And when I say blank, it's whatever that number is. I'm just trying to save time. So now they're giving it to me not in probability notation. They're giving it to me in a sentence, common. We got to be able to go back and forth between both. Find the conditional probability that a woman is 65 or older, given that she is a widow. So I'm going to ask you, let's first write the probability notation. What is the probability that she's 65 plus meaning or older, given that she's a widow? Again, I'm going to go now. I know she's widowed. So that eliminates all of this piece of the table. So I know my total number of women that it could possibly be. Somehow I know that this woman's a widow. 11,080. I'm looking at her online profile or something, and it says that she's a widow. Well, how old is she then? Because she didn't want to put her age on there. What's the chance that she's 65 plus? 1180 on the bottom. Of those 1180, 8,636 were 65 plus. So whatever that is, pretty good chance that this profile of this woman who is a widow, there's a pretty good chance that whatever this is, there's a pretty good chance that she's 65 or older. Okay, what's the probability of a woman being divorced if she's in the 65 to 20 or 25 to 64 age group? So again, what is the probability that she is divorced if she is in that age group? That is just another way of saying given that she's in the 25 to 64 group. So I know she's in this group, so that eliminates all that. I know she's one of these women. And what's the probability she's divorced? How many of them are divorced? Oops. Sorry, my denominator was the 18,262. My numerator was the 1,091. And that's the probability of a woman being divorced if I know that she's in the 25 to 64 age group. Sorry. Lastly, what's the probability of randomly selecting a woman who is 65 or older and married? So here's what you would typically do, just by being robotic. Probability of being 65 plus if I know that she's married. And that's wrong. Why? It's not saying if I know that she's married. It's saying I'm randomly selecting a woman. I want to know the likelihood that she's 65 or older and married. So instead of a conditional probability, I slipped in a little and married. Okay, I ask myself, could I go do this probability times that probability? Not necessarily. I don't know if those events are independent. In fact, I'm pretty sure they're probably not. I'm probably way more likely to be widowed if I'm old, which means they are not independent. So I can't just multiply them. So you got a few options. I could go back here and use this rule. But I'm going to say I think a little bit of common sense can kind of help us out. What's our denominator? Did I know anything about the woman? No. I'm randomly selecting a woman. Well, that means the denominator is all of the women. I didn't know anything about her, so I can't eliminate any of these other women. So out of the 99,585, which ones are 65 and older and married? That's those gals. So 7767 out of 99,585, whatever that is the probability of randomly selecting a woman who is 65 plus and married. Okay, that's practice with the concept of conditional probability. Okay, I'm going to go back, and this is really a 5.3 problem. And I'm going to show it to you now because I think you need to see that I've got multiple different ways of solving different problems. Okay, test for the HIV. Accurately will detect the virus 99% of the time, which means 1% of the time, this test does not identify that you have the HIV. That's kind of dangerous. The test, which we would call a false positive. I probably should say false negative. It said I don't have it, but that's wrong. The test will also produce a positive result 8% of the time for people who don't have the virus. That would be a false positive. I don't have it, and yet the test says, whoa, you got the HIV, which is kind of scary. I'll come back and talk about that. Actually, we'll talk about it in class. When we do our Zoom, somebody remind me. I just want to try to keep the video a little shorter. If, in a certain population, 5% of that population has the HIV, so let's just say we're talking about, I don't know, a country somewhere. Yugoslavia. I don't know why. If I know 5% of the population in Yugoslavia has the HIV, what is the probability that a person who has tested positive actually has the HIV? Well, if they tested positive, they have the HIV. No, that's not true. 8% of all my tests are going to give me false positives. So, and in your mind, this starts to get tough. I got the HIV. I got no HIV. I got a positive. I got a negative. I can't really draw a Venn diagram for that situation, but it's a decent thought. So what we're doing here is called a tree diagram, and all the tree is an organizational tool to kind of put all of these possibilities together. And the reality is there are 4 possibilities. I either got HIV or no, 2 options, and I can test positive or negative. 2 more options. Those are the 4 situations that I can have. Meaning there's going to be 4 different probabilities I'm calculating at the end of this. So, starting here, I'm going to begin with my first possible situation. You either got the HIV or you don't. Well, I also need to attach the probability of this happening. And because I know that 5% of the population has the HIV, I know that this is going to be 0.05, which means that this has to be 0.95. If 5% of the population has it, that means 95% doesn't. Well, now, within this subgroup, I could test positive or negative. If I have the HIV, I'm going to get a positive result 99% of the time. And I'm going to get a negative result 1% of the time. If I don't have the HIV, I still could get a positive result. I still could get a negative result. It's telling me it gives me a false positive 8% of the time. Again, watch out for your decimals. That'll cause you problems. And that means I get a negative test, a correct negative 92% of the time. One of the biggest mistakes I see is you guys stop there. You've identified it as a tree diagram and you stop there. I have not done anything but organize my information. The information I really want are the probabilities of both of these things happening. So 0.05 times 0.99 gives me 0.0495. I got to make sure I'm trying to remember numbers, and I don't want to lie to you. I need these ones. Good. And 0.05 times 0.01 gives me 0.0005. So we talked about a false negative. The probability of getting a false negative by randomly selecting somebody is 0.0005. So that's not going to happen very often, which is why we like that number being so big. Well, down here, 0.95 times 0.08. 0.95 times 0.08 equals 0.076. And 0.95 times 0.92 is 0.874. Okay, a little thing you can do at the very end of this. These are all of those 4 things I talked about. A correct positive, a false negative, a false positive, and a correct negative. So the reality is that and that are when this test works correctly. These are when it's jacked up. Well, if that's all 4 possibilities and you've done this tree correctly, all 4 of these had better add up to 1. It's just a way to kind of double check yourself at the end. Well, I've organized this. I've got my probability of my 4 different events. I still haven't answered the question. What is the probability that a person who has tested positive actually has the HIV? So I got to think about what that means. What is the probability that they have the HIV if I know that, because they have tested positive? That's a known statement. If I know that they tested positive. Okay. Again, I like to, if you want to play with the formula and try it that way, go for it. But I care about all of the people who tested positive. That's going to be what goes on my denominator. Well, these guys tested positive. So did these guys. So those are all the people that tested positive. So I got to combine those to get my denominator, 0495 plus 0.076. And of those, which ones had the HIV? These ones. So 0.0495 0.0495 divided by, make sure you put the bottom in parentheses when you do this, 0.0495 plus 0.076 equals, and I end up with 0.39, sorry, that's an equal sign, 0.3944, or about 39.4%. Okay, let's think about this for a second, because it's kind of a little bit of a shocking, mind-blowing answer. I go to the whatever, I get tested. I'm Yugoslavian, I go get tested. I come back with a positive result. It is not time for me to go bashing my head against the wall and a rampage. There's only a 39% chance that I really have it. What? You tested positive? Because there were so many false positives, a positive test doesn't necessarily mean we're the end of the world. You got a less than a 50% chance of actually having the HIV. And I think that's a little mind-blowing. It gets you a little bit. But if you think about it and look at it, it does make sense. So much more of the population didn't have the HIV, and we have such a higher rate of false positives than false negatives. Now, think about it, because this is more common sense logic. Why? Why? We want our test to be hypersensitive. I would rather a false positive than a false negative. Why? Because this mistake, both of these were mistakes, remember? This mistake is what I deem to be a much more dangerous mistake than this one. If I get a HIV test and it comes back negative, I think I'm good. What's that mean? Well, now I'm going to go be promiscuous and share needles and not protect people, and that is not a good thing for our society. If I get a false positive, we likely have a process where we're like, wait a second, we know there's a lot of false positives out there, so let's do another test, or let's go to a fancier, more sensitive test. Okay, and again, that's a 5.3 problem. It'll be a couple days before you get to there. These are just a kind of a little hodgepodge of other problems that we could play with. And I'm going to go fairly quickly. Actually, you know what? I'm just going to do them. And I'll try to keep it quick since I'm already at 27 minutes. Got a 90% chance of getting an A on the small exam. 73% chance on the big exam. There are 3 small exams, and I need to get A's on all 3 in order to get an A. So I got a 73% chance of getting an A on the one large exam, the final. I need to compare that. So that's the final. I need to compare that. Is it equal to, bigger, or smaller than getting an A on all 3 little ones? Well, to get an A on all 3 little ones, I would have to get an A on the first, an A on the second, and an A on the third. They have told me that these events are independent. Assume all the exams are independent, which allows me just to do the 0.9. This is the ghetto rule from 5.1 times 0.9 times 0.9. Didn't have to do anything fancy. And when I do this, I end up with 0.729, I believe. And since 72.9 is a little bit less likely than 73.1, I'm just going to take the final. In reality, the difference between those 2 probabilities is essentially nothing, so it probably makes no difference, which is why the teacher made it that way. The probability that DJ is late to class is 1/5. I'm being nice to you, DJ. What is the probability that he's on time all 5 days? So I got 5 days in a row. Now, I didn't write it in here, and I kind of do this intentionally. I think it was a mistake at first, but I've left it because I like it. So first of all, they tell me the probability he's late, but I need the probability he's on time. Sorry. Well, if the probability that he's late is 1/5, the probability that he's on time is 4/5. Yeah, but that's only for 1 day. I need him to be on time all 5 days. Well, there's a 4/5 chance he's on time on day 1, and a 4/5 chance that he's on time day 2, and 4/5, and 4/5, and 4/5, or 4/5 to the 5th. 0.8 to the 5th equals 0.3279. It's really, hang on, 77. It's really 3268, whatever. We tend to take these answers out to 4 decimal places. No really reason why, it's just kind of common. Depends on what you're talking about. The smaller your probability, the more decimal places you'll want to have, type thing. Okay, in order to do what I just did, and this is the piece where I made the mistake. Did I tell you that his attendance from day to day was independent of one another? His on-time probability. I did not say that they were independent, and yet I just used the rule that assumed they were. And that is super, super dangerous. That was the intent of the problem, but I should have had to say that they are independent. Because they are probably not independent. If he's late 3 days in a row, do you think that might change his likelihood of being late on day 4? I've yelled at him, I've kicked him in the butt, I've called his mommy. He's probably more likely to show up on time on day 4 and day 5. So I'm assuming they're independent. One day being late doesn't affect the next day, but that's probably in real life not true, even though that was the idea. Number 7 is basically the same. I'm going to kind of keep it. Sorry, Keefers. Transatlantic cable has repeaters, pulse the signal to get all the way across the Atlantic at regular intervals. The probability that a single repeater functions for its 10-year life is 99.9%. Assuming that repeaters fail independently, that's a big word, I like to see it. It allows me to use the ghetto multiplication rule. I don't got to use any of the fancy conditional stuff. What is the probability that all 300 repeaters that it takes to cross the Atlantic work for 10 years? Well, I need that repeater to work, and that repeater to work, and that repeater to work, and that repeater to work. Isn't that just 0.999 to the 300th? I don't really want to write out 300 of those. And we end up, I'm pretty sure it's like 75 or 6%. 74%, so that ends up equaling 0.74. You have about a 74% chance of getting all 300 of those to work for the 10-year life. And again, I think that one's a little bit tough to think about, because the chance of a single one working is super likely, but the chance that I get 300 of them to work, not quite as likely as I might have thought. And why do I care? Well, if I've got to go replace a repeater, I got to go out in the middle of the Atlantic, dive down, find it. It's probably going to be a pretty expensive task, and that might affect how much I'm charging to install this transatlantic cable. Diagnostic test for AIDS has a 0.005 chance at producing a false positive, so 0.5%. If 140 employees of Reno High are free of AIDS, what's the probability of getting at least one false positive? That's a big if. Just kidding. What's the probability of getting at least one false positive? Okay, so I mentioned this in the 5.1. Sometimes it's easier to find the thing you don't want. So the probability of at least one positive test result, aka a false positive, means I could get one false positive, or 2, or 3, or 4, or 5, or 6. There's too many possible things for me to calculate. So what is the only thing that would screw this up? We call this the complement. That's the same as 1 minus the probability of no false positives. And this is a much easier thing to calculate. So I'm going to do 1 minus the probability of not getting a false positive, meaning a correct negative. And again, we're assuming we are all free of the HIV, because if we don't know that we're all free of the HIV, totally different problem. 1 minus a correct negative, 1 minus 0.005, so I'm going to write it. 1 minus 0.005. That is the likelihood of getting a correct negative result, but I need all 140 of them to be correct, and I end up getting 1 minus 0.995 to the 140 equals about 50%. And again, gosh, that is not a very good chance of getting a false positive, and yet there's about a 50-50 chance that I'm going to get at least one false positive. Okay, I'm going to stop because that's plenty of, I'm sure you're bored to death. Put marks on any of these that you have questions about. We can talk about them during Zooms. B-Day kids, I'm sorry that this didn't work for you, but I would still watch it. I think it's probably good for you to fill out the notes and maybe get some clarification. Take care.